Good morning. This lesson is for my Honors Integrated 1 class, but before I get started, I want to say I hope everyone is doing all right out there. This is lesson 12.2, and we have two goals for this lesson, so let's go ahead and jump right in. Our first goal is going to be to review graphing linear inequalities. Our second goal is going to be solving systems of linear inequalities. So I wrote a table on the board. Hopefully this helps us to remember what the symbols mean. I'm going to shade below, look at how I wrote the L, I'm going to shade below if I have this symbol or this symbol. This symbol means my line will be solid, so the solutions are included on the line. This symbol means I have a dashed line, and that means the line is out of bounds for solutions. Solutions can't be on that line. If I have this symbol or this symbol, I'm going to shade above. If I have this symbol, that means my line is solid, and that boundary line, solutions are included. This boundary line is dashed, and the solutions are not part of the line. So I also want to point out the shading is where the solutions are. Okay, so I have three examples here that I'd like to work through, and I gave you an example in slope-intercept form, an example in standard form, and an example when I have one variable. So I'm giving examples of each of the types of linear inequalities that we could have. So let's just go ahead and jump right in. Remember, I graph using slope and my y-intercept. I begin at -3, 1, 2, 3. I move up 2, right 1. So up 2, right 1, I get to here. My line is solid. And since I have this symbol, I'm going to shade above. Now, you can shade in different ways. I like to just draw a few lines coming off of my line. But again, in the shaded area is the solution. So, for example, if I was to plug in 0, 0, I would get 0 is greater than or equal to, this becomes 0. So 0 is greater than or equal to -3, or 0 is on the right of -3. That is true. And again, this reinforces that the shading is where the solutions are. If I was to plug in anything out here where it's not shaded, I would get a false statement. Let's just do that real quick. So if I was to plug in this point, 0, -4, that means I would have a -4 for my y, because that's my y value. And then that would be greater than or equal to, my x was 0, so that goes away. And I get -3. Is -4 greater than -3? No. And if you're not sure, we can look at a number line. And this number line, or we can interpret this as a position, is -4 on the right of -3. No, -4 is left of -3, and that's false. And this is false because it's not a solution, and it's not a solution because it's not in the shading. All right, so let's move on to our next one. I need to get this into slope-intercept form, and I didn't realize that I needed to do this before I drew the graph, so let me erase the graph. Put this in slope-intercept form. So let's see here, -2x. So I was just thinking maybe I'll have you guys graph using intercepts, but not today. So remember, when I divide by a negative, what's happening is you're switching the position of numbers. And when you switch the position of numbers, you have to change the description of where the numbers were. So now I'm going to have y, instead of being greater than, it's going to be now less than. And I can get rid of the negative, so it's 2 over 3, x minus 4. So now let's graph this thing real quick. So I go down to 4. I go down 4 because my y-intercept is -4. I go up 2, 1, 2, and I go to the right 3. So 1, 2, 1, 2, 3. My line is dashed, and I'm going to shade below. Now if I was to plug in the point 0, -4, 0, -4, that means that I get 12 is greater than 12. 12 is not greater than 12. That's false. And that's false because solutions are not on dashed lines. Right? So let's move on to the last one. And I actually, before I do, if I plug in 0, 0, I get 0 is greater than 12. That's false. So again, the solutions are in the shading. If I was to plug in any ordered pair down here where the shading is, I would get a true statement. I would have a solution. The last example, example 3, I have one variable. And remember, when we have one variable, we make 2 ordered pairs, and we use the variable in the ordered pair. So I know the value of my y, it's -2. I can pick any values I want for x. I like the value 1 for x, and I like the value 2 for x. So let's see here. 1, -2. That was terrible. That was terrible. 1, -2. 2, -2. My line is dashed, and I shade above. Okay. So these are examples of lines in slope-intercept form, standard form, and one variable. I wanted to turn standard form. This is why I remember I wanted this problem. I wanted to turn standard form into slope-intercept form, and I wanted to divide by 0 to remind you that when you divide, you change positions, and when you change positions, you have to change descriptions of where numbers are. So this is this takes care of our first goal, review graphing linear inequalities. The second goal is really easy. I'll be right back. I'm back. All right, so we're moving on to goal number 2, which is solving systems of linear inequalities. Now, it's really easy to do, and I'm just going to, I have an example on the board with 2 linear inequalities. So this is a system of linear inequalities, and all we have to do to solve these is graph both on the same graph. All right, that's what we're going to need to do, graph both on the same graph. Now, remember the solution is where the shading is, right? So this one we're going to shade below, and the line is solid. This one we're going to shade above, the line is dashed, and where the shading overlaps, that is our solution, right? So make sure we have this written down where the shading overlaps. That is where we have our solutions to both inequalities. I wrote it differently than I said, but nonetheless, the idea is the same. All right, so this guy, I'm going to graph this one in purple. I have a slope of -3/1, and I have a y-intercept of 5. My line is solid, and I'm shading below. 1, 2, 3, 4, 5. I go down 3. I go over 1. So I start here at 5. 1, 2, 3 over 1. My line is solid, and I shade below. And you'll see why, in this example, I don't go crazy with the shading. It kind of makes it hard to see where the answer is going to be if you do that. So I graphed this one in purple. I'll put a purple box around it so we know that it was done in purple, to reinforce that concept. The next problem I will graph in blue. Now this one I want to remind you, there's no number in front of the x. We have a 1/1. Now if there's a minus x, it's -1/1. So I just wanted to include that, and I'm going to graph this in blue. I begin at -3. So 1, 2, 3. I go up 1 over 1, so up 1 over 1. Right, and my line is dashed. And I shade above. So again, I want to reinforce that the solution is where the shading overlaps. And I will color the overlapping in a third color, so we hopefully can see that this is where my shading is. Now that I know where it overlaps, I can shade a little bit more heavily, so it's very clear that any point that I pick in here will make both of these true. All right, so for example, 0, 0, great point to plug in is in there. So if I plug in 0, 0 here, I get 0 is less than 5, or 0 is less than 5. That's true. So that's the solution to the purple inequality. If I plug in 0, 0 here, I get 0 is greater, or 0 is right of -3. That is also true. So where the shading overlaps is the solution to both. That is the second second goal. Pretty simple to do. Again, remember, we're just graphing both on the same. So there are some situations where it might be kind of tricky to understand where the solution is, but try your best to interpret what's going on. I think that'll do it for this lesson. Again, I hope everyone's doing all right out there. Bye-bye.